So I'm really excited to talk about this paper dealing with hydrogels and using them for creating basically these octopus-style tentacle manipulators that are both strong but also soft enough that they're able to hold an egg yolk underwater. And so we'll dive into that now. And so this paper is on octopus-inspired self-adaptive hydrogel gripper capable of manipulating ultra-soft objects. And so you can find it it's published in nano micro letters, available on Springer Link, and the download link is in the notes below. And so what they've done is they've created these based off of this bio-inspired octopus tentacles, created a number of 2 degrees of freedom tentacle effectors. And so by 2 degrees of freedom, they can control the curvature of these artificial tentacles, and they can control the suction cups, the closure of the suction cups, using basically pumping water in and out of channels on these tentacles. So they use hydrogels, which are a really interesting substance. They're a polymer, and through these polymer chains, so it's basically a plastic, when submerged in water, the hydrotrophic components on that polymer attract weak bonds to the weak H bonds with the water, and so that bonds the water and immerses the water into it to really give it volume and shape, and give it the pliability, the flexibility, because there's lots of squishy weak H bonds that are inside of this polymer, that then allow it to squish and move around, and becomes great in an underwater environment, so they can keep that pliable shape, which is really important for them. And so what they've done with this paper was interesting, where they came up with some solutions for how to really come up with a very strong uh, uh, polymer hydrogel that allowed this level of flexibility that they were needing. And they did that by tuning the kind of contrast between the strong H bonds and the weak H bonds. So you can see here the inspiration really for their design with these octopus tentacles, and the 2 degrees of freedom that they're interested in using. One is the bending of the tentacle, the ability to wrap around things, and then the other is the suckers, that ability to suck on to something, as well as release it. And so that's really what they're showing here on the right in B, where they're able to pump water into this back spine and water out of the front spine, and that allows for a curvature, basically expanding the back, shortening the track along the inside, and sort of like a track, a racetrack, where you have a shorter path on the inside that then curves it inwards for the bending. And then similarly, they have a separate internal track inside this hydrogel tentacle, where then the water is pumped in and out of the suckers to give the alternating between concave when water is sucked out, and then convex to push it out when it's sucked in. And given the compliance of the hydrogel, that sucker will be useful. I think that's always one of the challenges in anything that's suctioned underwater. Because of the non-compressive nature of the water, it becomes you don't get compliance because of the expansion of the air. But in this case, it would actually be the deformation of the hydrogel that would give that compliance and expandability. They're showing here how they created these, and so they 3D printed these hydrogels with these different channels in the device. So you can see here the platform where they had basically a curing solution using UV light to cure the initial structure, the initial polymers, and then submerge that in deionized water to actually allow the water to flow in and create the various weak bonds to go from this orthogeno hydrogel into a hydrogel. Did a bunch of strength tests to understand how it breaks and elongates, where its young module is, its toughness, tensile strength. But then ultimately, what I find really fascinating is the ability to very gently hold something underwater, such as an egg yolk. So both having the strength that's needed to grasp onto things that are strong, wrap around things, but also the delicate precision to hold that egg yolk is really impressive. Yeah, they then went into doing some things specific for the strength test of the suctions. One of the things I'm more interested in actually the flexibility of the hydrogels and what they are doing with that. I think that's more interesting. To necessarily grasp onto something that is nice and smooth in an underwater environment is not always straightforward. And so I'm less convinced of some of the applicability around the suction, but certainly the ability to evolve shape is really fascinating. This stuff I find particularly interesting for what they've done. I'm interested in thinking through any time that you have a dynamic seal in an underwater environment, whether it's a shaft seal or of any sort, whether it's piston or rotary. That's a real opportunity for both wear as well as failure modes. I think that there could be some real applicability for this kind of technology for glider vehicles, for vehicles that are autonomous. I mean, in autonomy, you want to really be focused on energy efficiency. And so a vehicle that has an ability to modify its shape from control surfaces through to actuation, but without having the wear and tear that you would get through a rotary seal, I think that that's where hydrogels could have some real interesting applications over the coming years in the underwater robotics space. So that would be exciting to see.